All right, so sorry for the delay. The Wi-Fi was being annoying. And people on YouTube, please let me know if it's slow or lagging because I am on the guest Wi-Fi thing. But yeah, otherwise let's get started. So first, in terms of logistics, we have two things that are coming up for you in terms of assignments. So first, we have the project proposals that are due October 6th. I sent a reminder about that on Piazza. Please use the template that we've provided. If you haven't used LaTeX before, it's a good time to learn it and follow all the instructions in there. If you want any feedback on your projects before the proposal, you can go to any of the office hours to see if your ideas are feasible. And of course, we will get you back feedback after you submit the proposal as well. Homework 1 is finally released. It has you basically implementing a transformer encoder using primitive modules, layers, and PyTorch. So, you know, it is fairly simple homework, but if you haven't used these libraries before, it's a good learning experience. You should also be very familiar with the actual implementation of the transformer for things like the exam. So make sure to understand everything you're doing. The code that you're writing could also be extended into training a language model. Currently, the task is highly simplified, so it's more like a classification task at every position of the sequence. But if you added a mask, like an attention mask like we've been talking about, we could easily extend that into training a language model. And maybe we will do that for a subsequent assignment. Okay. And one other thing is we don't have that many classes left before the exam. So starting on Wednesday, I'll, at the beginning of class, just go over a few practice problems from some of the previous exams, just so that you have an opportunity to see like what could be on the exam and ask questions about those concepts. Okay, any questions about any logistics stuff? All right, really want to check on here to, okay, looks like it's all good. So let us proceed to today's lecture where, that's annoying. We will be talking about kind of two different things. So the first is how do we use a transformer to solve various tasks? There are many different configurations of a transformer that you need to know. And so we'll cover that first. So this ranges from decoders, which is what we've been talking about, to encoders, kind of hybrids between the two, and then encoder-decoder structures as well. So we'll cover that in the first part of class, and then we'll kind of zoom out and talk about kind of the different stages in language model training. So everything we've talked about till this point is focused on pre-training, and your exam will focus entirely on concepts associated with pre-training. But I did want to highlight the differences between pre-training and post-training and kind of talk about how we can differentiate the two so that we have a clear roadmap for post-exam when we start talking about post-training. All right, so let's get started. First, oh God, that is not the right thing. Oops. Okay, so we're going to talk about transformer configurations. And we'll just start with the one that we've been talking about so far. So when I have my prefix, favorite LLM is. I take the embeddings of these, and I'm going to send all of these into this box, which we can call masked multi-headed self-attention. And I will repeat this block L times, meaning I will stack L of these transformer blocks on top of each other. Note that this box contains a lot of stuff, right? It is representing the query key value projections, the attention score computation, the weighted average of the value vectors, concatenation of all the different hidden states, the feed forward layer that takes that concatenated vector and smushes them into a lower dimensional, the Z vector, and then the residual connection on top of that. So there's a lot of stuff going on in this box. Thankfully, I will now just draw this box instead of writing out all of that stuff. And at the end of all of this, we are left with our final Z sub i's, right? So the hidden states that are output from the final, at the final transformer layer. Each of these is fed to the softmax to predict the next word. What are we going to do today? So we can actually, let's do one we haven't done before. Today is going to be Quen. Okay, so this is what we've talked about so far in the class, right? And this is like kind of the dominant language model configuration that we see today. It's very useful for any task that can be cast as a text generation task, which, as we all know, anything that we put into ChatGPT is considered a next token prediction task. And so for whatever tokens that the model is predicting, we're going to consider it an instance of this kind of masked multi-headed self-attention task during training. So as we'll see, there are modifications of the mask that we can make to, for example, if my input contains a prompt, it doesn't make sense to mask the prompt or compute a loss over the tokens in the prompt, because I'm not interested in predicting the next word in my input sequence. I only want to produce the output sequence. So we'll get to that in a bit, but this is the one that we've talked about so far. So the mask is that kind of diagonal mask that we discussed before. So the other thing that we can talk about is an encoder. And so the encoder has just one fundamental difference. So I can just copy this whole thing. Oh, didn't do copy the output, but erase this. Okay, and erase this stuff in here. Okay, so the only difference between an encoder and a decoder in terms of computation is that the encoder uses completely unmasked multi-headed self-attention and stacks these blocks on top of each other. And so at the top layer, we are left with these Z vectors, the hidden representations. Now, I can't use the vectors at the top layer here, these Z sub i's at the top, for next token prediction. Why not? Why can't I use these vectors for next token prediction? Yes.
Since it's unmasked, like you're embedding knowledge in the future.
Exactly. So here, the representation associated with favorite includes information about LLM and is, right? Because we did not apply masking. So the query vector associated with favorite can always look into the future when computing the representation. And so if I had this model predict LLM at this time step, it wouldn't actually learn anything about language. It would just learn how to isolate the embedding of the next word and predict that. So there's nothing useful about this model when predicting the next word. So then what is this kind of configuration useful for? It's mainly useful for computing representations of full pieces of text, right, where you're not interested in generating a response or completing a text, but rather you're interested in doing something on top of an existing piece of text, like classifying the sentiment or some other kind of task where the input is a text and the output might be like a single label, or as you'll see in your homework, it could be a label at each point in the sequence. So just for some context, your homework asks you to solve a very simple task with a transformer encoder, which is you're given a sequence of text, a sequence of characters, and in each position, you're asked to compute how many times has this character occurred before the current position and after the current position in the sequence. So it has to predict a label, either 0, 1, or 2. So it's a highly constrained problem. You can predict this count at every time step. It doesn't require any masking or anything like that. You observe the full sequence. But you're still doing some sort of classification task that involves the full sequence, not just completing it. So let me just summarize why this might be useful. It's useful for computing representations of an input sequence. And so when I say representations here, just to clarify, I'm generally referring to the Z1L, that's a Z, Z2L. So these are the final layer output vectors from the last transformer block. And these representations can be used in other applications, such as text classification. And importantly, you cannot easily generate text from these models. We likely won't talk about it in this class, but diffusion language models rely on architectures that look very similar to transformer encoders, and there are ways to generate text from even a pure encoder model, but we won't get into that in this semester. In general, this is not the model that you would like to use when generating text because of the masking, the lack of masking. So some common examples of encoder models, probably the most prominent that you might have heard of is BERT. How many of you have heard of the BERT model? Okay, so almost all of you. There are variants like Roberta and even Electra. And now they're kind of coming back in the form of diffusion language models, or at least as a piece of a diffusion language model. We'll come back to this towards the end of class. I will go over the training objective for BERT and how it differs from the next token prediction task that we've been discussing. But it's good to know that you can just, with changing nothing but the mask, change a model from an encoder to a decoder. Then finally, we will talk about what's called the prefix LM. So this is the most common kind of usage of LLM today, where part of your input sequence is a prompt, and the other part is the response, and you're likely going to train over this concatenated sequence of prompt and response and not generate any of the prompt tokens. So here we can kind of broaden our example. So we could say something like, I don't know, answer the question. So this is our prompt, and then our, or I could say something like, what is your favorite LLM? All right, I don't actually like this example. Let me just erase it because it doesn't do a good job separating the prompt and the response. Maybe I'll say something. Okay, this is better. Complete the phrase. My favorite LM is Quen because. Okay, so here we have some prompt tokens and we have some response tokens. And so here, the main difference is that all of this stuff gets thrown into the language model, but the mask is changed to be partially masked, multi-head, self-attention. And so here, we get a bunch of vectors in response. I don't know how many drew here. Okay, and then here we start predicting the next word at this is token. So maybe we'll do something like Quen, comma, because, and so on. So these tokens associated with the prompt, no loss computed, and each prompt token can attend to all other prompt tokens. Okay, so we're gonna kind of break down how the mask looks in this configuration, but the intuition is like, if I'm giving an instruction to my language model, I only care to train the model to predict the response, right? So there's no need for me to predict the next word in the actual instruction itself, like complete the phrase, right? That's already assumed given to us by the human user of this model. The only thing we care about is training the model to predict a good response to this input. Yeah.
So seeing this, I just got a new thought that what if it is something like my favorite LLM is colon and when because. So something addition to what we have been discussing so far like in the first class.
Yeah, I mean, here I just wanted to make it clear that the prompt includes, like here it's clearly an instruction, right? It has this complete the phrase, which is more in line with how this prefix LM is used, the prefix mask in practice, where you have an instruction explicitly. My favorite LLM example is more of a like completion, the next word prediction task is implicit in that, but here, I just wanted it more aligned with actual usage of this mask where you have an instruction in the prompt. That's all. But yeah, it's kind of in our running example, the task is implied to be just predict the next word. But we're not treating any of those tokens as like special prompt tokens. So that's a difference.
So in the general scenario, we will be removing those special tokens while doing the prompting.
Which tokens?
Like in general, my favorite LLM is the colon and the
Oh, you're asking specifically about the colon?
yeah.
No. So in the this actually we will talk about on Wednesday, but it really depends on what your tokenizer is doing. So which is like, how do you take the input sequence and split it into words or subwords or characters that are then embedded in the model. So it's usually the case that the punctuation, like a colon or a comma or period, is its own separate token that will be embedded as a separate part of this sequence. Yeah, so we don't throw them out or anything like that. Yes?
So in our decoder-only case, then also decoder all three.
Yes. So that's a good point. In the decoder-only setup, the loss is computed on all of the tokens in the input because we're not doing this like unmasking on any segment of the input. Other questions? Yes.
Would we get like a similar output if we just put the same text to a decoder?
Yeah, it's a good point. So like, when we parallelize these computations, we will end up computing hidden states for all of the masked positions as well. We need to because the tokens that we're predicting need to have some context over what the prompt was, right? The idea here is that your prompt representations can perhaps be richer because they include information about the full instruction, not just what came before, which might give the model more context when attending over those representations in the completion part. So let me just show you how the mask looks in this case, and then it should be more clear. So the difference in the two is, well, I guess we can write out the mask for all of these. So the decoder mask we already looked at is something like this, where this top part is set to -infinity, and the bottom left is unmasked here. So we talked about this when we were discussing the parallelization of the, and just to clarify, here, these are like positions in the input sequence, so I can write it out like this. And so basically, you can interpret the rows here as what is our query vector, and the columns as what is the key vector. So here, for each query vector, we are only looking at the key vectors that are at that position or before. So this we already covered. Just for completeness, we can write out the encoder mask, which is just completely unmasked in the same way. So this is looking at everything. So every token, the query vector can look at all of the tokens before and after. And now we can look at the prefix LM mask, where things get a little more complicated. So I'll make it a little bigger here. So here we actually have some prompt tokens, P1, P2, P3, and then we also have some completion tokens, C1, C2, C3, and so on. So maybe I'll write that out here. And so in this case, first of all, we want all the prompt tokens to always look at all the other prompt tokens, right? So for this block over here, we're going to be completely unmasked, right? Now, similarly, we want the completion tokens, C1, C2, C3, all of those to always look at the prompt tokens, right? So this part will also be fully unmasked. Now, the only thing that we need to be careful about is, so we don't want any of the prompt tokens to look at any of the completion tokens, right? Because that would be cheating. And we also don't want the completion tokens to look at other completion tokens that are in the future. So our mask here looks something like this, where this part is unmasked and everything up here is set to minus infinity. Okay, and before I take questions, I just want to, for some terminology, because you might see this decoder masked referred to as the causal mask in literature. And so every time you see that diagonal mask, it is associated with the case where you want to predict the next word and you don't want the model to attend over future tokens. In this prefix LM mask, we also see the causal mask applied to one block of this attention matrix. But we have, these other fully unmasked blocks associated with the prompt tokens. Okay, yes?
So the prompt tokens are unmasked here?
Yes.
And the rest of them are masked?
Yes, that's right. So if you are a query vector at a prompt token, you are going to be able to look at all of the key vectors associated with all other prompt tokens.
Okay.
Because we are not predicting a loss or you're not predicting a word and computing a loss at any of those prompt tokens, right? The whole purpose of the prompt tokens is just to serve as context for the completion tokens that we are generating. Does that make sense? The only reason we can do this is because we are not predicting next words at the prompt tokens. Yes?
What is the benefit of doing it like this? What if we use look at the prompts also like in masked version?
So are you saying, I have a prompt and I have a response. What if I just use a big causal mask? You can do that. It's just the intuition is that because you're not predicting words in the prompt, the block up here, this block, there's no need for you to have this artificial restriction that at position 1, I can't look at position 5 of the prompt, because we want each of those representations to kind of be fully contextualized with all of the information that we have at that point. And so here you start out with the prompt, so there's no reason to have this restriction. In practice, it's not clear like what performance difference you would get if you just used the causal mask entirely, because at least one of the prompt tokens will have full knowledge of all the other prompt tokens. But it does seem like it's just like, why would you limit yourself that way when you can have full information within the prompt tokens? So yeah, it's a good question. Yes? So that's a good point. If you've used like ChatGPT or whatever, you'll note that there's multiple types of prompts. There's a system prompt, the user prompt, or whatever they call it. Those generally, the system prompt is just concatenated to whatever specific user prompt, and they're treated as one large prompt. So yeah, that's a good question. Okay, other questions? Yes? We will get to that. So the encoder-decoder I haven't talked about yet, but we will get to that right after we finish taking questions here. This is not, but it is a good point. Like this kind of combines an encoder with a decoder all in one model, but we will see that you can separate them into two different networks. So an encoder-decoder structure has two different transformer networks. One that takes in the prompt, and the other one that produces the completion. This is a more unified way to do it, and there's been kind of many results over the years showing that you do benefit if you have like a separate encoder and a separate decoder versus putting them both into the same model. But now, it's just a lot cleaner and easier to just have one model and mess with the mask. So that's what people prefer. Okay, let me check on YouTube. Seems like things are working well on this guest Wi-Fi. Let let me go back here. All right, so now we'll get into something a little more complicated, which is the encoder-decoder model that I was just discussing. And so this you will also hear referred to as a sequence-to-sequence model. In fact, if you read the transformer paper that was assigned reading, you'll note that the model that was originally proposed in that paper is actually an encoder-decoder model, right? The paper was a machine translation system, and the encoder would compute representations of some input, like, let's say, French sentence. The decoder would then produce the English translation word by word. And so these were two separate networks, the encoder and the decoder, but they are connected together via the attention mechanism. So the decoder's attention mechanism can actually look at the key vectors and value vectors from the encoder. And this is called cross-attention, which is something that we will explore through lots more boxes and vector diagrams. So let me get started. So we'll continue with the machine translation analogy to explain this part, because I think it's the most obvious motivation of these kinds of models, and also the historical precedent of the transformer was originally from machine translation. Actually, also the original attention mechanism was proposed for machine translation. So it's, you know, kind of cool to think about how all of the stuff that we have now from ChatGPT and Claude and Gemini all just originated from people like kind of grinding on machine translation. And now the models can do translation, but also a lot of other things. Okay, so let's start with the encoder then. Now we know that the encoder and decoder differ only in the attention mask. So let's say I have a few tokens in French. So I'll just call these F1, F2, F3, because I don't know any French, so I'm not going to make a real example. And now we're going to put these into a box of unmasked multi-head self-attention, and we're going to put it through L layers here. And at the end of the day, we are left with these final layer hidden states. Now, on the right-hand side, we're going to have a decoder. The goal of the decoder in this translation example is to predict the English translation one word at a time. Therefore, we know we have to have this causal mask somewhere, right, because we're generating a sequence. So generally here, we might start out with our start of sequence token. Then I'll have the first English word, the second English word, and so on. So here, things get a little bit more complicated. So the first thing that I'm going to do in my decoder is, and maybe I'll write this below. So this is our encoder, and this is our decoder. So the first thing is something that we've seen before in all of our decoders of the past. I'm just going to put this into a masked multi-head self-attention block. And I receive as output the hidden states associated with that. Now, if I just stacked up L blocks of masked multi-head self-attention, there's a problem, right? My decoder is not looking at the encoder's representation. So if I'm using this for translation, my decoder currently has no knowledge of the French sentence that's input, right? Because they're not connected together. So the trick is, how do I connect my encoder to my decoder? So here, I'm going to create some query vectors. So Q1, Q2, Q3. I'm realizing I'm going to need a lot more space, so let me move this down. All right, that should be good enough. Okay, so now I have these query vectors, but I need my key vectors to come from the encoder representation. So I want to be able to look at the French sentence and identify, intuitively, like words that are aligned with the current word at whatever position I'm at, or get some context as to what the French input sentence was so I can actually do the translation. So on the encoder side, actually all of the operations that we're going to do are at the on top of the final layer Z vectors output by the encoder. So at the top of the encoder, I'm going to get my, I already used green. Let me use, and purple. Wow, it did a poor job here. Okay, let me use red. All right. Okay, it's getting a little messy. This down. Okay, so these are my value vectors and my key vectors. So now I'm going to compute the dot product between my decoder's query vector and all of the encoder key vectors. So at position 1, I'm going to compute these dot products. And at position 2, I'm going to use the same exact set of keys. And so the goal here is that my first, the masked multi-head self-attention down here, allows the decoder to look at all of the previous English tokens that it's generated. The next part of this is going to allow that decoder to look at all of the French tokens. And so this part is actually unmasked, but the keys are from the encoder, not from the decoder. And so that's why it's called cross-attention, because we have the query coming from one sequence and the keys and values are coming from a different sequence. Does that make sense intuitively? Yes?
For the next, like for Q2, you wouldn't consider anything about the previous English.
Yeah, that's a good point. So let's say I'm doing Q2. Here I'm going to, I will not consider Q1 in, the key vector associated with position 1 of the decoder. I'm considering the same 3 key vectors as in the first time step. Yeah, that's a good question. Other questions? Okay, so, just to complete the picture, the value vectors are also from the same encoder sequence. And so when I compute the representation at the top here, so let me just draw this out. I was using purple, so let me stick with that. So all of this is an example of an unmasked multi-headed cross-attention block. And so this gives me 3 new vectors. Now, there is a problem with this setup. So my value vectors for this cross-attention come only from the encoder sequence. So while this, I need a new color. Don't know how to get a new color, so maybe I'll use brown. So these value vectors, these hidden states here and this one here, they contain different information. So the one on the bottom has information about all of the previous words in the in English, in the decoder side. The one on top knows nothing about the previous English words, but has information about the input French tokens that the bottom representation doesn't have. And so the way that we combine this cross-attention representation with the causal mask self-attention down below is we use a residual connection. So let me just draw it over here. So I'm going to take this representation and this representation and add them together. And actually, I will do the same for the input here. So I take the, actually, let me draw it over here. So this input is going to be added to the output of this block. So each of these, the decoder stacked 2 blocks, each of these has a residual connection, and that residual is critical to propagate information both about the previous English tokens and all of the French tokens that are input. So this is a little complicated, so I'll pause here and take any questions that people have. Yes?
Query vectors which are masked
Mm-hmm.
access to all the key vectors which are
Are you talking about the cross attention? So in cross attention, there's no masking happening. So Q1, Q2, Q3, they have no access to any of the decoder side representations. The keys and values come from the encoder. Oh, you mean like the query? Yeah, sorry. So the way you get those Q1, Q2, Q3 is to project the output of the previous masked multi-head self-attention block.
if it's French to English, I have access to only the previous bits of my English sentence, but the entirety of the French.
Yeah, in the second block, the cross attention block, the query vectors are formed from the output of the first block, which is the masked multi-head self-attention. But note that the output of the cross attention block has nothing to do with the query vectors. It's a function of the value vectors, right? The value vectors are the ones that are getting averaged together using the attention scores. The value vectors have no knowledge of the decoder's input, right? They're strictly from the encoder. So the residual connection is the only thing that allows information from English and French to combine together. Any questions about that? Yes.
So what are we? So we're adding these. So we're adding the 3 things together to, and what do we get out of that?
So at the end of the day, we get that z sub I vector, right? And so let me just complete the picture, and then we can see if people have more questions. So the decoder block actually takes both of these 2 modules and stacks these L times. So it's a little bit more complicated than a normal block because it's actually doing both masked multi-head self-attention on the decoder side and unmasked cross-attention over the encoder side, adding up the representations with this residual connection. And finally, at the topmost layer of all of this, to answer your question, we get our top level z vectors, and these we are going to use to predict the English translation. So here I'm going to predict E1, predict E2, and predict E3. Okay, so I know this is a lot of stuff, so please ask questions if you have any. Yes?
So the first E1, E2, and E3 are random regions.
Sorry, the first.
The first E1, E2 that we chose in the bottom are randomly chosen?
Oh, okay. So that's a good question. When you're training a model like this, the encoder-decoder model, your training data is actually like a pair of sequences. So you have an input sequence, which might be just all in French, and you have an output sequence, which is in English. So when you're training the model, you know the ground truth, let's say, translation. So you can do all of this in parallel. Like you know the E1, E2, E3 that correspond to the correct French translation. Yeah, so it's a little different than in training a language model where you only need one sequence. Here you actually need two sequences for each training example.
So if you have the correct like answer in the beginning, how is this training going to happen?
So remember that even though we have the correct answer, we want to train the decoder to predict word by word the translation. And so if you look at the bottom block in the decoder, this is doing masked self-attention, right? So each prediction has no knowledge of the future token. So at the first time step, I received the start of sequence token. After all of this computation, I'm trying to predict E1, right? So this purple vector at the top here, this one, it has no knowledge of E1, right? It has knowledge of the start of sequence token and all of the French tokens, but not E1. So all of this convoluted machinery is designed to get this representation to have information about all of the French tokens and all of the English tokens up to and including this position. Yes.
So the whole reason of doing the decoder encoder is to build this way to like train the model while we have the answers.
Yes. So you might be thinking, well, it is a lot simpler if I just use this prefix LM and I combine these sequences together and then I use one model and all I have to do is change this mask and everything is fine. And you are correct. But there is some intuition that, well, maybe if my input is in a completely different language than my output, it would benefit from having a completely new set of parameters. So that's why this architecture was dominant until about when like GPT-3 came out. And then people realized that, well, if I train my model in this way with the prefix LM and the inputs and outputs are of many different languages, the model actually can learn to both encode and decode text in multiple languages with just one gigantic model. So these prefix LMs, since they only have one model, which is essentially like a decoder, they are a lot easier to train. You can scale up the layers, like add more parameters in the single network instead of kind of dividing them across two half-size networks. Also with this encoder-decoder model, you need to kind of make decisions on, well, how big should my encoder be? How big should my decoder be? How many layers should, so it's more hyperparameters as well. But it is very important to understand this concept of cross-attention, because if you ever want to hook up an existing language model to, say, like answer a question about an image or a video or some external source of input, you need to allow your language tokens to attend over this external input. That will always be accomplished via cross-attention. Yes? Yeah. That's a great question that applies to all of these configurations. So the question is basically, at some point, your model will get so large that you can't fit it on one GPU. And so if I'm paraphrasing correctly, how do you like compute the loss and backprop it through all of these different parameters that might be sharded across multiple GPUs? There are some great libraries that do this now. There's a lot of work on model sharding, splitting the parameters, accumulating the gradients. So basically you'll have like some master process that splits the, you could split the computation by data if your model is small enough, or by model. So you might have some layers going to GPU 1, some to GPU 2, and so on. And there's a lot of libraries, like Deep Speed, for example, is a very popular one that handles all of this for you. But yeah, like there's a lot of engineering effort going on now on how you can make this kind of multi-GPU and actually even multi-node training. Things get a lot more hairy there. And you can imagine if your model is actually an encoder-decoder model, it might be even more complicated to do this kind of splitting up because you have to do the cross-attention as well. So yeah, I don't know if these libraries actually support encoder-decoder models at this point, but yeah, I would look into Deep Speed if you're interested in learning more about that. Yes?
Probably you would get to it later. So at inference time,
Mm-hmm.
at inference time, the first input will be the start of sentence
Yes.
only, and then it would do it like sequentially.
Yes, great question. So at inference time, in this kind of setup, I have the entire French sentence, and my decoder starts with the start of sequence token. And then I do like all of the computations, like the masked self-attention, which obviously can only look at the current position. Then the unmasked cross-attention, which can look at all of the French tokens. Then at the top, I produce E1, and then I put it back into my network as input, redo these computations, and proceed. Just like in a normal decoder-only transformer. Here, it's just we have our encoder computations have been done once and cached, right? Because we will always be reusing these key and value vectors at the top of the encoder. There's no need to recompute them every time. Other questions? All right, let me check. Okay, and how are K and B produced by the encoder? Are they also just two different projections of the L layer's encoder output? Yes, exactly. You are totally correct. The K and V at the top of the encoder are we looked at the equation for how to get the key and value vectors. It's, K is F of WK times the last layer's Z vector. So yeah, good question. Okay, great. So I think at this point, oh, what did I just do? No, that's not what I want to do. At this point, I hope to be done with all the complicated block drawing diagram. And now if I were to draw a encoder-decoder model, I would just abstract all of this into two boxes. One masked multi-head self-attention, the other unmasked cross-attention, and then draw this dotted line over. Okay, so just to clarify in response to the question asked on YouTube, cross-attention always uses the representations, or maybe I should say uses keys and values computed from the final layer Z vectors of the encoder. All right. Great. Any final questions about these transformer configurations? Okay, so now I wanted to kind of zoom out a little bit, and now that we talked about how to train transformers, how to set them up, all the different ways you can connect them together and do things, how are these configurations used in practice, and what are the kind of different stages of training? So we haven't really talked about this at length, and I just wanted to highlight where we're going for the rest of the semester. So broadly, there are two stages of training. So there's pre-training and post-training. And both pre-training and post-training use the machinery and algorithms that we've talked about up till this point. So we're always going to be using transformers. We're always going to be using gradient descent and backpropagation. We're going to be doing, like masked multi-head, self-attention, and so on. The differences between these two are really in their goals and the type of data used. And so, we'll start with pre-training and then describe at a high level what post-training is, but we'll go much more into the post-training process after the first exam. All right, so let's start with pre-training. Pre-training is conducted with as much text as possible. So these days, we're talking about trillions of tokens, and they're mainly derived from internet crawls. So there's the common crawl, which is a very large source of data. There is a lot of time and money put into filtering these internet data sets to get rid of like low quality gibberish pages, get rid of duplicates. As we'll talk about later on in the semester, duplicates can lead to a lot of issues with language model training, and gibberish as well can lead to even like giant spikes of the loss, which we'll see some cool logs from industry labs where they are just struggling to understand why their model's loss was like going down and then spiked up to like some huge value at one batch. And a lot of those can be localized to like very low quality training examples where the model just didn't know how to deal with that. Also, these days, yeah, sorry.
So, we're considering a bunch of common crawl and potentially trillions and a ton of duplicates potentially. I'm assuming that also then leads to potentially the ability of the model to start memorizing as if you have an insane amount of duplicates in your data, right?
Yeah.
That causes your transformer to go, whoa.
Yeah, so there's, intuitively and empirically, a connection between how many times you see some text during pre-training and how well the model has memorized it. And when we talk about memorization, we really have to be clear that there are many viable definitions of what it means to memorize something. What we generally care about is the model able to like regurgitate some text verbatim if you give it like a prefix of that text. And so things like, the Declaration of Independence, and observed probably tens or hundreds of thousands of times in the training set, these will always be verbatim memorized. And it's not clear that that's a bad thing, but nowadays we see all the LLM companies with copyright lawsuits, right? Because they've been training on books or proprietary data that has been acquired through dubious means, and some of these book authors are like, well, I put the first paragraph of Harry Potter into my model and it generated the next paragraph, and so that's clearly bad because it's regurgitating copyrighted data. I will add that here is like another source of data, which is generally copyrighted things like textbooks or novels. These, and this is just a big aside, but the training on this kind of data really improves the capabilities of the model. And so there's a question over, is it fair use of one of these, like say OpenAI, to train their model over copyrighted data if the model is not intended to regurgitate like the paragraphs of Harry Potter, but rather just improve its general language understanding capability. So that's still being litigated today, but it's very interesting, and we will talk about like this memorization versus generalization trade-off later on in the semester. Another thing I want to highlight is that here the general consensus so far is to train the biggest model we can afford. And now that might be changing recently. We might have hit the limit of how far we can go with just brute force scaling up the model and data size. But still, like the models that are used to, like GPT-5 and Gemini 2.5 Pro, these are much larger models than what we have in generally with the open weight models. Although there are some huge open source models now too that very difficult to run on normal people hardware. Okay, so one difference between pre-training and post-training is scale of data and model. The second is maybe even more important is the goal. So the goal of pre-training and the goal of post-training are very different. So let's outline some goals. At a high level, the goal is to obtain a model that understands many linguistic properties. So at this point, we are not aiming for a model that can solve a bunch of different tasks like math problems, coding, translation, summarization. That's not the goal. The goal is we want a model that has some powerful general language understanding capabilities. So this might mean, like it understands the grammar of many different languages. It's memorized some world knowledge in its parameters, right? So if I asked it, for example, the president of France is blank, and it completes that correctly, then it has understood a fact about the world and encoded it into its parameters. Another thing is what we call emergent properties. So these are properties of a model that only emerge when it's big enough and trained on enough data. And we will talk more about these later, but one such property is in-context learning. So this is the case where I want the model to solve a task, so I give it in the prompt like 5 or 10 input-output pairs of how this task should be performed. And then I give it a new example, and the model, if it's large enough and trained on enough data, can actually kind of learn the pattern from the examples that you gave it in the prompt and kind of generalize from that to solve new tasks. So this was the big finding of the GPT-3 paper. Before that, no one had really looked into, we can just put examples of the task into our prefix and the model will kind of learn how to solve it. And it's since been a huge driver of progress in LLMs. Another one that you might have heard of is this chain of thought behavior. So a model can, if you ask it to explain how it solved a particular problem or task, it's able to do so and improve its performance on certain things like math problem solving. This is a behavior that seems to emerge in the pre-training process once the model is large enough. So I will just briefly contrast this with post-training because we're not really going to talk about post-training too much right now. We will talk about it extensively after the exam. But the goal is very different. the overall goal is to, one, make a pre-trained model better follow instructions. So there is a difference between being a good next word predictor and being a good follower of human instructions, and that's like one of the main goals of post-training. Another goal is to align the model to human, very related goal and values. So here you have like all sorts of safety training. You know, you might not want the model to produce offensive content or copyrighted content or things like that. And so that's also one of the goals of post-training. But really the main thing is we want the model to be good at following instructions. And just as a bit of contrast, generally we're using much less data. Well, I shouldn't say much less at this point, it's not clear, but we're using less data than pre-training. Definitely not doing post-training over trillions of tokens. We might be using more compute though, as we'll see. That is kind of post-training compute is closing the gap with pre-training compute. And some methods that we're using are fine-tuning, which we'll talk about next time. You will commonly see this abbreviated as SFT for supervised fine-tuning, reinforcement learning. And so this is a case where you don't have like exact input-output pairs to teach the model how to do something, but you might have a way to score its outputs instead. So if you say, you know, solve this math problem, and it outputs a bunch of text, you can maybe have some sort of function that looks at the answer that it's produced and tries to judge if that's correct or not. And you know, the model might generate a lot of text before coming up with the answer. This could be like the chain of thought, but only the final answer that it produces matters in terms of you know, deciding if it did a good job or a bad job. So you don't have to understand any of that right now. That is something we'll talk about next time. I just wanted to end this class with a quick example to make the difference more clear. I hope this works because the internet got messed up, but let's see. I'll put this screen capture thing on. Let me just copy this. So I was trying this out beforehand. Okay, so hopefully you can see this. So here I have two models set up. So one is this Llama 3.1 405 billion parameter pre-trained model. So this model has undergone just pre-training and no post-training. And then I have this Llama 3.1 405B instruct model. So this is the exact same model, except it has gone through both pre-training and post-training. And so I don't know if this will actually work, but let's see. I can generate outputs from both of these models, and we can take a look to just get a qualitative sense of the difference between a pre-trained model and a post-trained model. So this one, this is the base model. It's only undergone pre-training. The prompt is, write a 10-sentence story about unicorns. Each sentence must begin with the letter U. Each sentence should be numbered on its own line. The fifth sentence should include the word tremendous. And so the pre-trained model doesn't just follow my instruction. In fact, it continues my instruction. It says the story must involve a cat, and then it produces like 12 different other constraints about what the story should be. So obviously, I'm the one giving the instruction. I don't want the model to just add more instructions. It seems to like actually follow this, although the fifth sentence does not include the word tremendous, so it failed in that regard. It also does an analysis. So like none of this is what I wanted, right? This is just too much. And yeah, I don't know what this is either. Okay, so here's our post-trained model, which you can see wrote 10 sentences. The fifth sentence does in fact contain the word tremendous, and it seems to be about unicorns. So the post-trained model followed my instructions, all of the constraints, didn't do anything extra. And so this kind of motivates why these two phases are there. You can see that the pre-trained model, it's not like it didn't do anything relevant, right? If you were asking it to predict the next word, this is a totally valid thing to predict, like continue predicting instructions. But it's just not what we as the user of the model want. And so that's why we also want to have some post-training. All right, so next class we will continue with a kind of high-level diagram of the pre-training, post-training pipeline. We will talk more about BERT and how training BERT works. And finally, we will spend the rest of the class talking about tokenization, so how we split an input sequence into individual tokens that get fed into these models. So yeah, see